So in other words, when we talk about the spatial and space part, and this is extremely important, so I'm going to write this down on board, because this is the key when we explaining the space part. So now these matrices, when you derive it, these matrices, before I erase them, could you guys write this down? This will be quiz 5. In other words, quiz 5, could you guys write this down? It's going to ask you to derive from this equation here, from this equation all the way to this equation down up to here. So in other words, these will be derivation. Could you write this down? In other words, start from there, from our identity matrix, all the way derive to this point. So this will be one of the questions will be on the quiz number 5. Okay, you got it? So that's what we have. Now I want to explain what's a spatial and a space space. This is really, really important. And not only I worked on this quantum mechanics many years, still did not understand completely. I have to be honest. It's not completely understandable. But I want to show you, try my best. I want to show you what is the difference between this one here. For the spatial part, these 3 axes can be set perpendicular to each other. So in other words, x, y, z, they can be perpendicular. So there is no overlap. In principle, you can do like this. But now space, if you're in a space space, there is no such thing that there is no such thing like a sx perpendicular sy perpendicular sz. There's no such thing. There's no such thing that sx is going to perpendicular to sy and to perpendicular to sc. Even in the ideal situation, it's still maximized. It just gave you the expectation values. So for 2 reasons. There are 2 reasons why you cannot have like an axis project onto this. Just for 2 reasons. The first reason, the operator do not commute. We did not discuss this yet, so do not worry about this, but I did not discuss yet. Yes, I did not discuss this yet. I just over too much. We haven't talked about SZ, SX, SY. We don't know sigma ones. We haven't talked about it. Just one thing, at the operator level, they do not commute. Do not. They do not commute. Operator level, they do not commute. Second is more important, the eigenstate. Or eigenfunctions, I should say. They do not share a common eigenfunction. They do not share a common eigenfunction. If they do not share the common function, so there's no way you can put them actually perpendicular to each other. So this was a challenge. So whenever entangled with the spring space, it will be entirely different. Okay, I think that's all that I have. We don't have anything else. Oh, sorry. Okay, I want you to enjoy this particular graph. This is showing about its postcard sent to board. Did you see what time? February 8, 1922. That's more than 100 years ago. And this was his postcard. Did you see on the left, there's one single line? On the right, there's split. That's where the spin split's going on. Did you see at 2 ends, they just narrowed away, close. In between, there is no line in between this. This was a postcard. And I didn't realize the Europeans, they can't read German easily. I did not know it. When I was German, I thought, well, the German. And they said it written in German in this sense. So this means Bohr must know German, otherwise he won't be able to read it. And he had one sentence written in German. Bohr is right after all. So that's why Bohr somehow convinced this must well happen. And at the time, he was, well, you could have probably a massive line like this. And it's a such a nice picture, and I really want to share with you. Now, these are really, really good. And if you guys want to have slides, I will upload this slide for you guys as a record of this. Anyway, so that's, I think, all I have. Okay, we do not need to zoom now. Bye-bye, zoom. Focus on good. And the zoom now. So, and today our job is continuation from the Pauli matrix, which we discussed last time. I hope this way give you a little bit of more idea how do we do this. So this is the Pauli matrix, and could you guys check which item we are on? The item number 2 or number 3? I just get confused. 3, item number 3. So for the moment, it's item number 3. Good, good, good. So now, we're going to move on to the next item, which is quite a big change in the sense that for the moment, these are just Pauli matrix. It does not give you the entire idea of how to calculate the electron spins. So this is my item number 4, which we call spin matrix. Pauli matrix has no unit, it's just 1, 2, like has no unit. But now we need to attach the physics into that. The Pauli matrix, we use the sigma hat to represent the Pauli matrix. Spin matrix, we use letter S to represent it. Let's put the hat on the top. And we have a ratio h bar over 2. This over 2 is exactly Stern-Gerlach experiment tell you either get a positive 1/2 of h, usually called 1/2, h bar over 2 or negative 1 h bar over 2. And this is called a spin operator. And units will be in h bar. H bar is just angular momentum units, exactly the same way. Now the beauty of this 1/2. Did you remember when they permute? Did you see we have a 2 here? Did you see we have 2 here? When you're written in the spin matrix becomes simpler. Sx hat, Sy hat equals IH bar Sz hat. Did you see there's no 2 anymore? Because what we did was, see here there's no 2 now. What I did was that because we defined h bar over 2, that's why 2 is gone. Did you see that? That's the main reason. And then this will be is going to be the permutation relation, which is used, and this permutation relation. Let's go back to the Pauli matrix. The permutation relation, sometimes some books they're written in the following way. They use the I to J indexes like these, and then this will be twice. And they introduced a constant. This is called the Levi-civita symbol. This is a Levi-civita symbol, which means if you are in order 1, 2, 3 equals 1, 2, 3, 1 equals 1, that's fine. But anything that is a change the order, you get a negative 1. If your 2 indices are repeating, you get a 0. So that's the main idea. And this is just a side mark. It's not most important. Oh, parentheses. Not most important. Just give you a side mark. This is called Levi-civita symbol, which we have. Okay, so this is a sort of a relationship we have. Now, what we want to show you is the next part. Once we have a spin matrix, we will have its eigenfunctions available. But before we do that, I want to give you all the equation that is quite needed necessarily at this time. So I want to show you additional equations, which I'm going to write over here. And let me write down here will be better. So I also have S plus hat in the same way as they're like an angular momentum. X hat plus I sy hat. If I have a negative, I will have a negative like this, sy hat. So this is a negative. And this is a rising and lowering operator, similar way like what we did before. Just in comparison with the orbital plot, there's no difference for the orbital plot. There's no difference for the orbital plot. Exactly the same way here. I just said my time L, L, L. Here's L, L, L. L plus, L minus, L minus. And put a hat back. So everything just imaged one by one. So once you learn before those things, and you can calculate easily. Now, what we're going to show you, did you remember we talked about spatial and spin space? And we're going to parallel to this part. So just to impress you, spatial. Just spatially what we will do in the spin space, what we will do. So this is just a side mark, and then we will continue on this way. Spatially, this is the classical mechanics, similar in the quantum mechanics if you just like these vectors. And what we normally do, we have a component x hat. This is the unit vector, not an operator. A y, y hat, a z, z hat. And that is in the classical things we do like that. So here, ax, ay, az, it's just a single number. It could be a function, of course. Just a single number. So that's so in the classical mechanics, even quantum mechanics, when you derive it, it's just a single number. But now in the spin space, that's spin. We can also write down the spin in terms of these components. For instance, we can write an Sx hat. This is the unit vector in the spin space. We also can write it in the following way. Y hat, like this. And we also can write the following way. Z hat, like this. We also can write in the following format. And then we have in the spin space, a lot of x direction, y direction, z direction. Now this x, y, z, x, y, z, these are all referring to spin space. These are all referring to spin space. So essentially, you can compute the component along any arbitrary directions, and you get a matrix out from this. So that's how you do the calculation in this way. Now, the thing that is different here, these are Sx, Sy, Sz. These are matrices. These are matrices, not a single number. On the top, we have a single number. Bottom is a matrices. And this is compulsory. You have to use the matrices. Otherwise, it's incorrect, because spinning, you must use the matrices for this one. So now I'm going to show you some examples to show you calculate the eigen values and eigenvectors for some matrices. Let me show you the eigenfunctions, which this part is quite intense. In the beginning, when I was preparing the class today, I thought I'd ask you guys to read the textbook. But later on, I decided against this idea. I just want to have the one example explained to you. That way, you will have a better understanding what is happening here. Okay, very good. So I'm going to explain this, show you one example, and maybe two examples, And later on you will feel confident about this. So here our job is we want to find eigenfunctions of SZ hat. So this is our job. We are trying to find eigenfunctions of SZ hat, even though it's real simple, but I really insist we need to find an eigenfunction for SZ. Let me write an SZ in terms of matrices. This is a 1, 0, 0, negative 1. And this is the spin matrix which we have. In order to find the eigenfunction, what I do the following. SZ, and this is a matrix, so then I will have a component called A and a B. We don't know how large A, yes, go ahead.
Just double checking, you got the matrix from SZ hat from sig to Z.
Yes, yes. Okay. So the SZ here is just from the sigma. Sigma Z is just 1, negative 1. That's why you can see 1, negative 1. Yes. Now I'm looking for the eigenfunction. So therefore I'm going to multiply by a known vector equals to eigenvalue. I use the ampersand referring to eigenvalue. And this A, B. Like this. Okay, so that's what I did. So I plug everything into this equation. 1, 0, 0, 1. And I have A and B, epsilon A and B. Then I try to find the determinant of this particular equation. So I move this term, the right hand side to the left. So then what I have is the following. H bar over to minus epsilon. Remember, this only has up diagonal element. That's why I just put minus there like that. And this term is still 0. And this term also still 0. Now next term is H bar over 2 minus epsilon. And this will be A, B. And my right hand side is going to be 0. I just move everything from right to the left. I jump a little bit. Are you guys good? So what I did was essentially move this term to the left. Do you want me to add one more step? You want me to add one more step? Do you?
Yeah, I'm just confused on how you absorb the E without the A and B.
So
and the epsilon on the E side.
I talk about which step, from here to there, or from there to here.
So I get subtracting it over.
How do I get this one?
Yeah.
Oh, okay, sure. I can plug in one more step here. Sure. So I'm going to plug in one more step here. Let me plug it in. Where's my razor? Here we go. So I'm plugging one more step here. So I plug in one more step. This is H bar 2, 1, 0, 0, negative 1. A, B. Now this is the minus epsilon. Leave some space here. A, B. Here I can put identity matrix like this. This is what I did. And now when you put a identity matrix, this will be epsilon multiplied 1, epsilon, epsilon. So therefore you do subtractions. That's what the extra step. Are you good now? So this is the extra step which we do. So yeah, exactly. So now the determinant is just the coefficient of A and B. The coefficient of A and B, which means determinant, and we'll set this guy to 0, so there will be non-trivial solution. Otherwise, we will get a trivial solution, which doesn't make any sense. And this is just simple elements calculation. H bar over 2 epsilon multiply negative, negative, I put a negative in the front. H bar over 2 plus epsilon 0. This whole thing equals 0. Then you can see my epsilon has two values. One is going to be positive, one is going to be negative. H bar. And this is what I have here. So one is positive, one is going to be negative h bar, and that's my eigenvalue. Let me double check. Yeah, the equality is good. So now, once I got this, this means that the energy level of the eigenvalue 1 is going to be h bar over 2, negative h bar over 2. Now let's look at the eigenvector. For epsilon 1 equals 1/2. So I'm going to plug this guy back into my previous equation. That's what I'm doing now. So let's do that. So plug this one here, h bar over 2, 1, 0, 0, negative 1. And here's A and a B. This is epsilon equals positive h bar over 2. I get an A and a B like this. So I'm going to cancel these two terms out. This cancel out. So I'm going to cancel them out. H bar over 2, H bar over 2 cancels out. And then I do the matrix vector multiplication. So this will be multiply each other. So this will be 1 multiplied by A, give me A. All right. And the second one is 0, A, 0, negative B. So this negative 1 is negative B like this. So this will be something like this. Are we good? So this matrix, this time that, gave me A, 0 times A, 0, and then negative 1 times B, like this. So you see B has to be 0, right? B has to be 0, because B, positive B equals negative B. So B must be equal to 0. So A, now A equals A, like this. So A equals A. So far, we have not determined how large A is. Are we good so far? Did you get lost somewhere, Tobin? Are we good to get this eigenvalues?
So I got the eigenvalues, I understand.
What about? So this next step, you get lost.
This is you're trying to find the eigenvector, right?
Yes, right now try to find the eigenvector. Yes.
So you plug in.
Plug it into. Use this guy. Yeah, plug it into this equation here. Plug in this equation.
Oh, that one.
Yeah.
Okay.
Oh, yeah. I thought it was the one.
Yeah, I thought.
Oh.
Like, wouldn't that be 0?
I thought it was down one. I was like.
My gosh, sorry. Okay. I'm going to use. I'm so sorry. Red line here. This is the red ones here. And that makes crystal clear, so that's what I did. Okay.
So you're.
Yeah, I plug this guy into this equation and get that equation. Yeah. So this is the equation you see here.
Oh, okay. Yeah.
And this epsilon is just h bar over 2.
Okay.
So that's what I get. Okay. I'm so glad that when I struggled a little bit when should I include this or not, and eventually I said, well, I think it's best include that. That way at least student will know what that is. Are we good so far? So B must be 0. So now, so far A is still not determined. A is still not determined. We don't know how large A is. So the next step, what do we need to next step? What we do? What we do? How do we deal with A? Alex, how do we deal with A? A is unknown now, still we don't know it. And all the wave function must be what? All the wave function must be what? A word start with N. Exactly. All the wave function must be normalized. This is a condition which I'm not going to use right now. So all the wave function must be normalized. So then there is no other choice except I'm going to normalize this wave function. And this is what I'm going to do. So I'm going to normalize this wave function such a way that they gave me a 1, value 1. So this is, I'm going to do it right now. So let me move this one over here. So that way you can see a little more clearly. Yes, now I'll do the normalization. Let me erase this part. So I'm doing the normalization now. I'm going to call this wave function, let's call it psi. How about that? It doesn't matter, I can call this psi. And this is, let's just use a direct notation psi. So now the normalization means the psi has to equal the 1. That's a normalization. Let me write this down. This is so important, normalization. The broad part, which means this is the kid part. Broad part means I need to rotate them. So this part will be A. B is 0, so I don't need to write anything out. The kid part, this is the kid part. This is A, 0. And that's the broad part. Yes?
So for direct notation, with the complex conjugate spot, we also transpose to, or not transpose, but...
Yeah, it just rotate.
Okay.
Yeah, it is transposed. It is transposed. You know,
Yeah.
whenever you see this guy's here, this means it's transposed.
Okay.
Just flip them over. For the vector, well, it doesn't matter if it's called transposed, just lie them down in the vertical, horizontal, like this. Okay, so that transpose. And then the kid part will stay as it is, so like this. Now you do the multiplication, and this, of course, this multiplied by that, it's just one element with a squared, like this. So this just gives us a squared. So then a squared just equals 1. Then my a just equals 1 like this. And if you say, can I just choose negative 1? You are perfect fine. There's nobody will blame you to use a negative 1. It's perfect fine. But people like a positive 1, so that will be fine. So then we have a wave function. This will be 1, 0. And that's our wave function. Now this wave function is unusual. So therefore we would denote this wave function called alpha. We denote this wave function called alpha. It's a 1, 0, and this is called a spin up wave function. This is called a spin up wave function. The electron spin up wave function. So that's why. In solid state physics, in solids, right now in atoms, we commonly use just spin up or spin down. In solids, in the magnet materials, and these are also called the majority spins. Also called the majority spins. So usually the points up we call the majority. That's called the majority spins. But it's not that important. Essentially just tells you the wave function. It's going to be up. So this is the for the eigenvalue epsilon 1 equals h bar over 2. Folks, why don't you go ahead and practice to find the wave function for this guy, negative h bar over 2. Give you 5 minutes or 3 minutes. Try to find what the wave function for the epsilon 2 equals negative half h bar. So I will give you the time. If you have questions, just let me know, so I will be more than happy to talk to you. Alex, did you turn in your homework? Please turn. You grab your old homework, please. When you're done, let me know. So I will be more than happy to check with your results. Oh, yes. Let's see whether you got it right. Yes, very good. Good job. Anybody else finished? Yeah, it's better when you work out the detail yourself, and then rather than follow just what I was doing. Okay, let's just wait a few more seconds. See there. I want everybody on the same page. Finished? Could you guys check with each other? Compare with each other. Compare with each other. See whether you guys get the same. Alex, are you finished also? Check with the other folks. Check with them. Check with each other. Check with each other. See whether you get exact same results. Did you get the same? Same? Everybody's got the same. All of you get the same?
Yeah.
Okay, very good. So, and then that particular state, which we call the beta, this will be 0, 1. And this is spin down state. And this is the spin down state. So these are the so-called the wave function for the spin ones. So that's the eigenfunction. Now we have eigenvalue. We also have eigenvector, also called eigenfunctions. And that's what we needed. Now let me summarize it, because before we show you additional things. Here's the summary of wave functions. Sometimes now we call it spin wave functions or total wave function. Let me just write total wave function. Total wave function. Total wave function. And now, because these states that I normally have the alpha, it's this state here, beta that state. So you're going to see we have two parts. One first part is the spatial part. That's spatial part of wave function. Let's call it phi of r. That's the spatial part of wave function, which we have here. That's spatial part. And then we're going to multiply by the spin part of wave function. In the book we use eta. This is the spin part. So this is the spin part of wave function. And this is called the direct product of these two. These two are completely isolated in the sense that you can apply them separately. So this will be phi, and this eta, just multiply by each other. And that's the summary of the total wave function you will get from this. Now, what we will use, we're going to use this equation to show you even something even more interesting, and this is which is very important. For the moment, you see when I found the eigenvalues, I write down the eigen equations, Did you see when I find eigenvalues here, I just solve these matrices like this way. There's a different way to solve these eigenvalues. It's a different. Do you see we have a S here? Let's do S dot another S. Just do the dot product. When you have a dot product, you totally have 9 terms, right? 1, 2, 3 times another 1, 2, 3. You totally have 9 terms. However, only non-zero ones, these ones only non-zero because of a unit vector. Y hat dot y hat equals 1. Z hat dot z equals 1. All the others is going to be 0. So therefore, we only have 3 terms remaining. We have sx squared plus sy squared plus sz squared, like this. So we only have these matrices, survives. So these matrices survive. Because every of these matrices have h bar over 2, so therefore you will see h bar over 2 parentheses squared, like this. Okay? And this is what we have. Now the remaining part, for instance, this is going to be sigma x squared. Folks, I want each 3 of you do calculation. One student, let me ask, Tobin, could you calculate sigma x squared? And Aisha, could you do the sigma y squared? And Alex, could you do z squared? In other words, the matrix squared, matrix term itself. Okay. And so then when you guys are done, come to the board, maybe come to the board, tell me how large this one is. Tell me how large this one is. Tell me how large this one is. So remember, we have matrix directly. So this is the Tobin, this is Aisha, this is Alex. So matrix multiplication. When you got an answer, you look at your answer, ooh, like this. Then you just need to get a correct answer. When you look at your answer, you will go, ooh, like a shock.
You just want us to tell you?
Yeah, just come over. Write this down. Write this down. Which one is yours? Yeah, that one's yours. Okay. Cool, thank you. Thank you. You find it strange. It's the identity matrix. This guy's squared is equal to identity matrix. This is just incredible. Remember, we just only need the sigma y times sigma y, sigma z times z. Whenever you're done, just let me know.
That's why.
Yeah, sorry?
I just.
You finished? You want to write that on board? Oh, you got it. Yeah, go ahead, write it down. Write it down. Go ahead, write it down. Yeah, just write them down. I gave you a red pen. Write that down. Yeah. Okay, thank you all very much. Do you find something strange? Regardless of what you do, they all equals 1. This was built by design. Remember, in the beginning we said this A matrix times A matrix equals identity matrix. That's why all of them equals 1. So this will be 3 times of this, right? 3 times this. So therefore, folks, we will have 3 in the front. And then you have 1, 0, 0, 1, like this. And that's what we have. This means I have eigenvalue. This is already diagonal now. There's already diagonal. There's no need to rediagonalization. So this will be 3. With my razor here. Write a little smaller. 3 over 4 h bar squared. 1, 0, 0, 1. So I'm going to write an eigenvalue on the top. So the eigenvalue of s squared, because this is already diagonalized. The eigenvalue is this part, 3, 4 squared like this, right? And then you say, well, Dr. Zhou, that's the end of it. I like it. So that's 3 quarters. Not quite. I want to move one step further. Folks, 3 quarter can be written as 1/2, 1/2 plus 1. Right? 3 quarter I can written as 1/2 times 1/2 plus 1. Sure? Okay. So you good? That's 3/2 times 1/2, of course, that's 3 quarters. H bar. And then Dr. Zhou, what are you doing? Well, you see, so far so good. There's no difference. Now, what to calculate? S plus 1 h bar squared. If I let S equals 1/2. 2. This S is called a spin quantum number. It's just a number. It's classical. It's not operator. It's just a number. And you may wonder why, what the big deal here is. What is a big deal? Well, here's a big deal. I'm going to have to erase some of those ones. Now, if you compare this expression with our L squared, YLM, and this just L plus 1, h bar squared YLM. Did you see the similarity between these two? Did you see the similarity between these two? They are exactly the same. That's why when the people, wow, the spin part is actually just like an angular momentum, except its quantum number now changed to 1/2. While the orbital part, this L equals 0, 1, 2, keep on going like that. This is half integer. This is integer. So the spin part, this 1/2, that's why split to 2. That's the key idea comes out. I hope you like this. This sort of everything bring back to what we learned before. That's why this chapter 6 somehow, when we write a book, we struggle a lot. Which one is actually we want to resonate with the students? Because now you see, oh, okay, that makes a lot of sense. That's what we insist that time, and repeating the same thing again. The only thing that we did not show you here was that the wave function, but this wave function here, in the basis of the SZ, there will be 1, 0, 0. And now this, you see, this guy is the eigenfunction. This is eigenvalue. Let me write an eigenfunction. Eigenfunctions, this will be 1, 0, 0, 1. This will be exactly the same as my SZ. Because this is already the diagonal, so there's no need to do that. And can I just borrow 1 second? It's just real important. We showed you they have exactly the same eigenfunctions. And the main reason, I have to erase this part, it's classical, I don't like classical ones. The main reason is because these two, they permute with respect to each other. And this rings a bell to the chapter number 4 again. Two commutators share the same eigenfunction, like that. So that is a key reason. You see, this is so useful in this sense. That's why we emphasize many, many times. Right now, we didn't do anything. We just showed you. Then there will be exactly the eigenfunction. See you guys on Monday for the class. Of course, we have labs. So, all right, that's it. Any questions? Any questions so far? No question?